Hi students, welcome to Section-Shear lectures and welcome to the playlist on the advanced steel designs. In today's class, we shall see the design of the combined rectangular grillage foundation as per the limit state method IS 800-2007. In the previous class, we have seen the design of independent grillage foundation as per the limit state method IS 800-2007. I hope you are enjoying the discussions. Then don't forget to click like, share, subscribe and help our channel to grow further, right? Now, before we see the actual discussion, let us see the brief profile of the speaker. That is, I, Dr. Dirvesh Kumar, has obtained my BTech Civil Engineering from Nagarjuna University in 1994, MTech Section Engineering from JNTU Hyderabad in 2000, and PhD in Section Engineering from JNTU Hyderabad to 2009. Presently, I am working as Professor of Department of Civil Engineering, University College of Engineering, Osman University, Hyderabad, Telangana State. I have an experience of 28 years, of which 7 years is in industry and 21 years is in teaching at graduate and postgraduate levels. My research areas include reinforced cement concrete design, structural shield design, structural analysis, fight element analysis, earthquake engineering, bridge engineering, structural optimization. I published 45 research papers in international as well as national journals and conferences, and organized 3 international conferences and 11 national conferences and workshops, and attended 43 workshops, visited 2 countries, delivered 14 guest lectures and edited 3 books, and supervising 14 PhD scholars and supervising 30 ME theses, right? I am actively involved in various consultancy works that are offered by the department and completed over 800 plus design proof checks and 150 plus designs of the RCC, steel, composite, low-rise, high-rise, multi-story building, and that of the road and rail bridges, right? Now, let us see, in the previous class, we have seen this independent footing design student wherein I have designed just to go back to this previous problem. Yes, this I have designed individual footing, wherein in the top tire we have used IS MB series, as well as in the bottom tire we have used IS LC channel sections as beams, right? However, if I redesign this using ISMB in the lower tire, how this design will change, right? That I am showing, right? There's the same problem. I'll not go in detail because I already solved this. I just show change in numerics, right? Design a 2-tier grillage foundation for a column transmitting an axial load of 1000 kN. The SBC is 1500 kN per meter square, and the base plates are 700 by 700 mm square, right? This problem we have seen. Even we have designed, we have fixed this length and breadth, as well as we have designed the upper tire beams using 3 beams of ISMB 300 at the rate of 44.2 kg per meter, which satisfied all the criteria, right? It satisfied the check for the clear spacing, as well as even section class. From the section classification, we got the section as a plastic section, and moment of resistance of the each beam, moment capacity is greater than that of the factored bending moment to which it is subjected, as well as it satisfied the check for the shear also. And even this is how the shear resisted by each beam is greater than the factored shear force. And even we have checked now whether is it a case of the high shear. Yes, it is concluded that it is a case of high shear. Accordingly, we have reduced the moment capacity MD using this MdV is equal to MD minus beta multiplied by MD minus MFD. That worked out to be also okay, right? Even later on, we have check for web buckling also, check for web buckling and check for web crippling, right? However, coming to the top, the low tire, there we have analyzed, and we got the same design forces, factored bending moment as well as factored shear force. However, even we got the same plastic section modulus. However, we have provided there IS LC. Let me go back, right? That is we have provided ISMC 200 at the rate of 22.1 kg per meter, 10 beams. However, now if I provide IS instead of channel sections like this, right? If I provide the beam series, how the design will change. However, there is only change in numerics only, right? As per the IS 800 1984, either you may use channels as that or that of the I sections like this, right? Therefore, if I use now IS MB 175 at the rate of 19.3 kg per meter, right? Now we can check that even it is passing I'm not going through exact calculations now because they have elaborately explained, right? Now you can see that the clear spacing between the webs is 143, which is greater than 75 mm, and the check for shear is also okay because it is resisting, each of the section is resisting 126.3 kilonewton, whereas it is subjected to a factor shear force of 46.88 kilonewton only. And also, is it a case of the high shear? No, because 46.88 is less than 0.6 multiplied by VD 126.3, which is 75.78 kilonewton. It is a case of the low shear, therefore no correction is needed for the moment carrying capacity, right? And even if I calculate the moment carrying capacity, right, now the section is a plastic section. Even if I calculate the moment carrying capacity, right, of the each section, it works out MD given by this formula, right, 37.67 kilonewton, which is greater than the factored bending moment of 32.81 kilonewton. Therefore, it is also okay, and the check for web buckling. Also, because here d by tw is 25.05, which is less than 67, then the web buckling under the shear is not required. That is also concluded. And also check for web buckling, is over now. Check for web crippling. If I do as per this code specification, what I elaborately explained in the previous class, right, now I can find that buckling load for each of these section, right, web will buckle at a load of 1001.56 kilonewton, whereas the load coming onto the web is just 125 kilonewton. Therefore, it is okay. That is how now I am fixing 3 ISMB 300 in the upper tire and 12 ISMB 175 in the lower tire. With each length of the beam 2.8 by 2.8 meter as shown in this figure, right? Therefore, these are ISMB 300 and this is that ISMB 175, right? However, this length of the beam is just only 2.8 meter. We need to provide further 100 plus 100. Therefore, the total width of the footing is equal to 3 meter by 3 meter, right? And the size of this base plate is equal to 700 by 700, right? We can see that in the top tier beams, 3 ISMB are seen, and even in the lower tier ISMB 175 are seen, right? Each of these, right? Now 1, 2, that is how I'm just counting, so on and so forth up to 12th beam. They are put in a grillage or in a series, right? This is what the previous problem what we have seen. However, this is with ISMB series in the lower grillage, right? Now let me move to that of the combined rectangular grillage foundation. Now this is problem data student, 2 columns having the sections ISHB 400 at a rate of 82.2 kg per meter and ISHB 300 at a rate of 58.8 kg per meter, carrying an axial load of 1800 kilonewton and 1200 kilonewton, are placed 4 meter apart. The safe bearing capacity of the soil may be taken as 200 kilonewton per meter square. Design a rectangular grillage foundation, right? Right? This is how. However, in my previous video, ASD2 and ASD1 and ASD3, elaborately explain how to proportion the rectangular grillage foundation. Right? Or let me see this. I have just explained like this, right? Combined rectangular grillage foundation, how the analysis should be done, right? And how the proportioning should be done, right? And this is how the schematic should be done, right? I'm just recalling that. For elaborate discussion, you may revisit the previous videos, ASD1 and ASD3, right? This is how the load on the left column is transmitted onto the top tier grillage, which is transferred onto the lower tier grillage. Similarly, for the right column also transmitting a load of P2 kilonewton onto the base plate is transmitted onto the top tier grillage, transmitting the load onto the bottom tier grillage. Here the dimensions are assumed as the width as b, therefore this is b by 2. And here we'll say that from the center line of the column, the length of the beam is or that is actually a cantilever, not a net cantilever, is a cantilever a1, whereas a net cantilever is a1 prime. This is a1. And similarly to the right side, from the center of the load to the end is a2, right? This is a2, right? Now the center to center distance between the columns is c, whereas now we'll calculate where the CG of this combined grillage foundation is there, which is at a distance of x bar from the left hand side column, central line of the left hand side column, passing through this CG of this base plate, right? Therefore x bar, remaining distance is c minus x bar, right? And let the length of the footing is L, right? That is how. And let the size of the base plate, that of the left base plate is equal to L1 by L1, and that of the size of the right base plate is equal to L2 by L2, right? This we already explained, right? This is a net cantilever projection to the left side A1 prime, and net cantilever projection A2 prime. And how to analyze this we have already explained, therefore I will not go into this. And even how to proportion this, I already told that x bar is equal to P2 divided by P1 plus P2 multiplied by C, right? Once after getting this, now I'll find out the width of the foundation given by this formula. B is equal to 2 multiplied by C minus x bar minus plus A2. And then what is that length required is area required divided by B provided, whereas area required is equal to 1.1 multiplied by the total load divided by the safe bearing capacity of the soil. Once I do that, right, I'll find out what is the left hand projection A1 from the center of the column, which is equal to B minus A1 minus C, right? Then after that we will do the analysis as I have explained in the previous videos. V for getting the shear force V1 is equal to P1 divided by 2L1 L minus L1. Similarly under the second column, V2 is equal to P2 divided by 2L L minus L2. And the bending moments under both of these left and right columns are M1 is equal to P1 by 8 L minus L1, and under right column M2 is equal to P2 by 8 L minus L2, right? This is how I have explained elaborately. You may just go through that. Whereas for the analysis of the bottom tire grillage also analyzed at different section, right? At section 2.2, right, 2.2, wherein even by equating that is equal to 0, I got, right, where I'll be getting the maximum bending moment, right? Therefore at that I'll find out the maximum bending moment, for which I'll design. You may just go through this for further discussion, student. Now let me see a numeric problem. This numeric problem also we have seen using working stress method in the video ASD1 as well as ASD3. The same problem I am solving using now the limit state method in this video, right? Using limit state method in this video, right? This is the same problem. Two columns having ISHB 400 82.2 kg per meter and ISHB 300 at 58.8 kg per meter, carrying an axial load of 1800 and 1200 kilonewtons respectively. This is how the given data, student, right? Now what I will say is that I'll assume the Fe410 grade steel, for which ultimate strength of the steel is equal to 410 MPa and yield stress of the steel is equal to 250 MPa. If I go to IS 800 2007, table 5, page number 30. Let me go to that page number 30 of IS 800, student, right? Now we can see that this is a table 5 where it gives the resistance governed by the yielding gamma m0 is equal to 1.1 and the resistance governed by the ultimate strength, right? Gamma m1 is equal to 1.25, right? Therefore, I just noted down these partial safety factors, right? Then this is the column section under the first load, ISHB 400 at the rate of 82.2 kg per meter, transmitting a unfactored load, or the service load P1 is equal to 800 kilonewton, whereas the second column is transmitting a load of P2 is equal to 1200 kilonewton. That section is equal to ISHB 300 at a rate of 58.8 kg per meter. Therefore, these are the factored loads under left and right columns respectively. P1 factored load is equal to 1.5 multiplied by 800, 2700 kilonewton, and P2 is equal to 1.5 multiplied by 1200, 800 kilonewton respectively. Whereas the size of the base plate under the first column is equal to 800 mm by 800 mm, which is L1 by L1 is equal to 800. L1 is equal to 800, which is a square base plate, student, like this, right? Whereas under the second column, it is also a square base plate of 700 mm by 700 mm respectively, right? L2 by L2 is equal to 700 by 700, right? Then what now I'll do is I'll do the proportioning of the footing as a first subheading, right? Wherein now I'll find out what is the size, and I'll fix the different dimensions so that finally I'll arrive at the size of the footing, right? Therefore, the size of the footing, first I'll find out the CG. In the proportioning, I'll find out the CG of the footing of the grouping. Just now I explained by taking the load P1 as the reference point, right? The distance from that to the top, the CG of the load where it is acting is equal to P2 multiplied by C divided by P multiplied by X bar. Therefore, that gives X bar is equal to, upon substitution, right? Actually, these are the factored loads, even unfactored loads, even if you do, because 1.5 in the numerator, 1.5 in the denominator, both will get cancelled. Both will give the same result, right? If you take even the ratio of the factored loads or unfactored loads, it is material, right? Therefore, it is now 800 divided by 2700 plus 1800 multiplied by 4. The distance between the columns, two columns, is equal to, the distance between the two columns is equal to 4 meters. This distance is equal to 4 meters. Therefore, that CG will work out 1.6 meter. 1.6 meter. Now, assuming a cantilever projection of near the load P2, right side load P2, under that load A2 is equal to 1 meter. Then B, the width of the footing, right, is equal to 2 multiplied by C plus A2 minus X bar. Substituting the values, now I'll get 2 multiplied by 4 plus 1 minus 1.6, or say 6.8 meter. Width is 6.1 meter. However, what is the area of the footing required? Now I'll calculate that one. From that, now I'll calculate what is the length of the footing required. Therefore, length of the footing required is nothing but area of the footing required, that total load divided by the safe bearing capacity, that divided by width of the footing provided, right? Therefore, generally we'll take 1.1 multiplied by total load P divided by the SBC as the area required, right? If I do from that point of view, now I'll get say 1.1 multiplied by 800 plus 1200 divided by 2000, that divided by 6.8. Therefore, it now works out say 2.43 meters with 1.1, 10% extra for the sulfate, of the foundation generally, right? However, this being a combined footing of large dimension, now I'll try to check what is the sulfate of the footing, right? Because I'm getting a width of 6.8 meter. I'm assuming that I want to provide a length of 3.7 meter. With that assumption, now I'll find out the sulfate. Sulfate is nothing but 6.8 plus 100 plus 100, 700 centimeters or 7000 mm or 7 meters, because 100 mm will be the concrete. Concrete will be there beyond the end of the beams, right? Anywhere the minimum clear cover is 100 mm as per the IS 800 1984. Therefore, the size of the footing is 7 meter by 3.9 meter multiplied by, assuming say ISMB 500 beams. Therefore, here 100 mm, even the clear cover is equal to 100 mm. Therefore, the depth is equal to 700 for the first step, right? And that of the top tier grillage, right? We are providing, I am assuming that I want to provide 1 meter by 1 meter concrete pedestal, right? There are two such pedestals with an assumption that I want to provide say some 250 depth beams. Therefore, plus 2 multiplied by 1 multiplied by 1 is the plan size, multiplied by 0.35, that multiplied by 25 is the self weight of the concrete, plus the soil overburden pressure over that is equal to 7 multiplied by 3.9, from which I'll deduct 2 meters, 1 minus 1 meters for each of the pedestal, right? Therefore, that multiplied by, assuming the self weight of the soil as 19 kilonewton per meter cube, now I'll get 975.95, so approximately 1000 kilonewton is the self weight. However, this cannot be neglected. Therefore, if I take into account this 1000 kilonewtons rather than just assuming 10% extra, now we'll get the length required is nothing but 1800 plus 1200 plus 1000 divided by 2000 divided by width provided 6.8 meter. From that, now I'll get say a length as 2.94 meter with exact dead load calculations. However, I want to provide more, say instead of 2.94, I am assuming that yes, I want to provide 3.7 meter, right? Or even you may provide 3 meter also, it is a material, but not less than 2.94 meter, Therefore, I am just assuming a length of 3.7 meter, student, or even may assume 3 meters or 3.2 meters, that is left to you. If you want to optimize, it is better you just assume just small increment in this value, right? 2.94 or say 3 meter, 3.1 meter, right? If you don't want to optimize, then you may assume like this, right? However, here the optimization is not on the prime target now. Therefore, without that, now I want to proceed. Or even if you want to optimize, you may just assume 3 meters, right? There will be small saving in the material can be achieved, right? Therefore, I am assuming L is equal to 3.7 meter, wherein I don't want to optimize to that extent in this problem, right? The sections and the sectional stresses are the moment carrying capacities and the shear strengths, right? Therefore, with that, what is that length of the beam from the center line of the left column? A1 is equal to 6.8 B minus this A2 is equal to 1 meter minus C, that works out say 1.8 meter. Therefore, once I get this A1 as just proportion 1.8 meter from the fundamentals, therefore these are, now I'll get assumed A2 is equal to 1 meter. In the previous case, there I got B proportion. Therefore, using that same A2, now I'm getting what is A1, like this. Just let me show this schematic, student, right? Yes, not this one, just bear for a moment, right? Therefore, I assumed this A2 is equal to 1 meter. Now I got A1 is equal to 1.8 meter. That is how I have just done the proportioning in this very first step. Now the proportioning is over. Therefore, these are the results of this proportioning, that I want to provide a length of 3.7 meter and breadth of the 6.8 meter, and A1 is equal to 1.8 meter and A2 is equal to 1 meter as shown in this figure, right? As shown in this figure, right? A1, A2, C, right? B and L. Therefore, that is the very first step over, right? Once I conclude the proportioning step, now I'll go for the next step as the analysis of the upper tier beams, right? However, I want to analyze for the loads under the left column transmitting a load of P1. Therefore, V1 is given by the factored, all these are the factored shear forces and factored bending moments, right? V1 is equal to P1 divided by 2L multiplied by capital L minus small l1. Factored load is equal to 2700 divided by 2 multiplied by 3.7 minus 0.8. It is transmitting a factored shear force of 1058 0.1 kilonewton. Similarly, the factored bending moment M1 is RMU1 is equal to P1 by 8 capital L minus L1. Substituting the numeric values 2700 divided by 8 minus multiplied by 3.7 minus 0.8, it works out 978.75 kilonewton meter. Right. Therefore, once I do the analysis, now I'll go for the design. Wherein now I'll find out what is the section modulus required. Therefore, now I'll say that as for this IS 800 2007 class 8.2.1.2, page number 53, assuming the section as a plastic section and low shear. Let me go to this 821 to page 53. Page number 53, student, right? Let me just check 53. Just wait for a moment. 53. Yes. I'm there in that page number 53, student. Therefore, as per this, where d by t is less than 67 times epsilon, then even when subjected to the low shear, means not exceed VU not exceeding 0.6 VD. MD is given by beta B, ZP Fy divided by gamma M naught, where beta B is equal to 1 for plastic and compact section, or it is equal to Z, the ratio of the elastic section modulus to plastic section modulus for semi-compact section, and ZP and ZE are the plastic and elastic section moduli respectively. Right. Therefore, using this codal specification, codal provision of IS 800 2007, as per the IS 800 2007, right, 2007, from page number 53. Now let me this is my assumption. To start with, I have assumed low shear and the plastic section. Hence, now I'll say that section modulus required ZP is equal to how much. Therefore, substituting the numeric values is equal to MU is equal to 978.75 into 10 to the power 6 multiplied by, for plastic section, now it is 1.1 for plastic section modulus, it is beta is equal to 1, that divided by Fy divided by 1.1. Fy is equal to 250 divided by its partial safety factor is equal to 1.1. That now works out to say 4306.54 10 to the power 3 mm cube. Therefore, now this is my assumption that assuming 3 beams in the top tier beams, right? Assuming 3 beams in the top tier beams like this, right? Just I want to assume say 1, 2, 3, right? Therefore, what is the section modulus required for each of these beams is equal to the plastic section modulus required is equal to that 4306.54 divided by 3 into 10 to the power 3. It works out say 1435.51 10 to the power 3 mm cube. However, for trial section, you increase this value by 20% more. Therefore, the plastic section modulus required for the trial section is equal to 20% of this extra, this value 1435.51. It works out say 1722.61 10 to the power 3 mm cube. Therefore, now what I'll do is I'll go to IS 800 2007 table 46 page number 139, or alternatively you can go right to SP 61 1964 table 1 page number 2. Let me go to IS 800 page number 139, student. Page number 139. Yes, page number 139, right? 139. Yes, I'm there in the page number 139, student. Right? This is the annex H plastic properties of the beams. Right? These are given, right? Wherein now I am trying with ISLB 500 at 73.5. Let me see this ISLB 500 73 ISLB 500. Yes, ISLB 500 at the rate of 75.0 kg per meter. Therefore, I'll note down the relevant properties of this ISLB 500. Wherein it is furnishing a plastic section modulus of 1773.67 centimeter cube, whereas elastic section modulus of 1543.2, and the other properties are like this. That the width, the depth of the section is equal to 500, and the width of the flange BF is equal to 180, and the thickness of the flange is equal to 14.1, and thickness of the web is equal to 9.2. Therefore, I just noted down all the relevant properties. from this IS 800, or alternatively you can go to this SP61 ISLB 500, right? SP61 table 1 page number 2 ISLB 500, right? Now you can see here ISLB 500 at the rate of 75 kg per meter. The same sectional properties are shown, except we don't have the plastic section modulus in this SP61 SP61, right? Therefore, that is noted from IS 800 2007 as per the new code demonstrate method, right? Therefore, I just noted down this property, student, right? And what is also H2? H2 is 34.9. That also I have noted down, where H2 is the depth from the bottom of the section up to the end of the root radius, right? Therefore, which includes the thickness of the flange as well as the root radius up to the end of the root radius also, that H2, right? Therefore, total depth minus 2H2 is equal to the clear vertical depth of this web. Clear vertical depth of the web subjected to pure shear, like this, right? Then now let me check what is the section modulus provided. ZP provided is equal to 1773.67 10 to the power 3 mm cube, which is greater than this trial section 1772.61. This is okay, therefore it is okay. And also the elastic section modulus is also 1543.2 10 to the power into 10 to the power 3 mm cube, which is greater than generally the elastic section modulus will not be compared. Right? Just have noted down that elastic section modulus, student, right? 1543.2 10 to the power 3 mm cube. However, that will also be required for section classification, right? Now that's why I have noted down that value, right? Once prima facie it is okay, the section is okay, then let me check is it okay in all other criteria. Then first check is a check for the spacing. However, the clear spacing between these webs is equal to, what is this clear spacing, right? If I have three beams, right, therefore 800 is the width of the base plate within which I want to accommodate 3 webs of 180 mm width each. Therefore, then between 3 beams 2 spacings will be there, that divided by 2. Therefore, it works out, say 130 mm, which is greater than 75. Therefore, it is okay. First check is okay. Similarly, what is the next check? Next check is a check for the shear as per the IS 800 2007, class 8.4, page number 59. Class 8.4, page number 59. Therefore, if I go to this page number 59, student, let me go to this 59. Yes, 59, right? Yes, I am there in that page number 59. The factored shear force V in a beam due to external actions, V should be less than VD, where VD is equal to Vn divided by gamma m naught, where gamma m naught the partial safety factor is the shear failure, and Vn is equal to Vp is equal to AV Fy W divided by root 3, where AV is the shear area, Fyw is the yield strength, whereas for I sections and channel sections, which are for hot rolled section bending about the major axis, there for hot rolled sections AV shear area is given by H multiplied by depth of the web multiplied by its thickness. AV is nothing but H multiplied by TW. Therefore, substituting these into this formula, now I'll get the design shear force VD is equal to say Fy is equal to 250 divided by 1.1, that divided by root 3 multiplied by H, depth of the section, depth of the web is 500 mm, and its thickness of the web is equal to 9.2, that divided by 10 to the power 3. It works out, say 603.59 kilonewton. However, it is subjected to a factored shear force of 1058 divided by 3, because we have provided 3 beams. 3 beams will be resisting this much of shear force, right? Therefore, that works out, say 352.7 kilonewton. However, each of the section has a shear capacity, shear strength VD, or design shear force of 603 is much greater than the factored shear force to which it is subjected, 352.7 kilonewton only. Therefore, it is okay. However, let me also check, is it a case of the High shear, yes, check for the high shear. As per the IAC 800 2007, class 8.2.1.2, page number 53. Let me go to the page number 53, student, right? Let me go to this page 53. Yes, what the code says, just now we have seen. Yes, this is that page 53. Page 53, wherein page as per this page number 53, if uh, if the design shear force does not exceed 0.6 VD, then that is the case of the low shear. Then MD is equal to MD. Otherwise, MD is equal to MDV as per this class 8.2.1.3. Right? It should be taken as when V is exceeding 0.6 VD, then MD is equal to MDV. That we have seen already in the previous problem also. Right? Therefore, now let me check, is it a case of the high shear? Yes, right? Therefore, the shear force on each of the beam is equal to 352.7 kilonewton, and what is 0.6 VD? 0.6 multiplied by 6 not 3.59, right? It works out, say, 362.15, whereas 252.7 is much less than 36 is greater than 362.15 kilonewton. Therefore, it is a case of high shear. It is a case of high shear. However, you please see that there is a small change in this value. 352 is just greater than 362, right? In such a case, now I need to calculate MD using MDV. However, even in the previous class I have shown that for same problem, right, there is a small change, reduction in the MD value. Therefore, now I am not checking. Now to start with, I am saying that it is just neglected. Therefore, it is okay, very negligible, right? Or otherwise, you may see how to modify this MD value to MDV as I explained in the previous class, right? However, here this is a case of high shear, but even I am neglecting that effect because 352 is just greater than 360. I'm sorry, student. Right? 352 is just less than 0.6 VD. 362. Therefore, it is a case of low shear. Therefore, I need not use this class. Just what we have seen. Let me go to this class. Therefore, I need not use, right. Therefore, this shear force is not exceeding 0.6 VD. Therefore, MD is given by this formula. MD is equal to beta B ZP Fy divided by gamma M naught. Otherwise, if it is exceeding, then as per this, MD is equal to MDV. Therefore, here this value is not exceeding. I am sorry. Therefore, it is not exceeding. Hence, it is a case of the low shear only. It is a case of low shear because 352 is less than 362 is also okay, right? Then let me check for the moment carrying capacity. Design moment carrying capacity as per the IAS 800 2007, just now shown, class 8.2.1.2 from page number 53, because it is the low shear capacity. Therefore, first let me see what is the section classification as per this IAS 800 2007, table 2, page number 18. Table 2. Let me go to this table 2. Right? This formula just now seen, student. Right? Just now we have seen this formula. Right? This formula we have seen. Right, where it requires the section classification, whether the section is plastic or compact or semi-compact, right? Therefore, for which now I need to go to this page 18. Let me go to this page number 18. Yes, 18. Yes, I am there in that page number 18, where outstand element of the compression member for rolled steel section B by TF. If at all it is less than or equal to 9.4 times epsilon, then the section is plastic section. Even web of and I section, neutral axis at the middle depth. However, I am considering a symmetric section about the horizontal axis. Therefore, D by TW should be less than, if at all it is less than or equal to 84 times epsilon, then the section is plastic section or class 1 section. Let me check whether the section is a plastic or not. Therefore, I am checking that as per this table, B by TF. However, I do have the width of the flange is equal to 90. Width of the flange is equal to 90. Therefore, that divided by 2, 45. 45 divided by thickness of this flange. I'm sorry, right? Let me go to this. What is the width of the flange, right? Sorry, the width of the flange is equal to 180 mm, student, right? 180 mm. Therefore, that divided by 2 is outstanding length 90 mm. Therefore, that 90, this 90 divided by thickness of the flange 11.4. That now works out, say 90 divided by 14.1 is 6.38, which is less than 9.4. Therefore, the flange is a plastic section. Similarly, whether the web is it a plastic section or not. Therefore, d by tw, where d is nothing but h1. H1 is nothing but h minus 2 times h2. Therefore, h is 500 minus 2 times h2. H2 is readily given, or it is the summation of the thickness of the flange 14.1 plus h2 17, right? Therefore, that divided by thickness of the web 9.2. It works out, say 47.58, which is much less than 84. Therefore, the web is also a plastic section, Hence, the entire section is a plastic section. Therefore, beta is equal to 1. Hence, the design moment capacity given by this formula MD is equal to beta is 1 multiplied by ZP. The plastic section modulus provided 1543.2 10 to the power 3 multiplied by Fy 250 with its partial safety factor 1.1 divided by 10 to the power 6. It works out, say 350.72 kilonewton meter, which is much greater than the factored bending moment to which it is subjected is 978.75, which is shared by 3 number of beams. That divided by 3 means 326.25. However, the design capacity, moment capacity is equal to 350.72, which is greater than 326.25 kilonewton meter. Therefore, it is okay. It is okay. However, now I'll go for the next check. Check for web buckling. As per IS 800 2007 class 8.7.3.1, page number 67. Page number 67, right? And as well as even if I go to this class 8.2.1.1, page number 53. First, let me go to this class page number 53, students. Right? Page number 53 is 53. Therefore, I am there in the page number 53. However, now the code says that the design bending strength of a section which is not susceptible to web buckling under the shear before yielding means when d by tw is less than 67 times epsilon naught shall be determined according to this 8.2.1.2. Right? This is what we already done. We have found out MD using that. However, therefore, let me check whether this d by t is less than or equal to 67 or not. Then the code says that it is not susceptible to shear buckling. The web is not subjected to shear buckling. Therefore, we already obtained d by t w in the previous subheading here, right? D by tw is equal to 47.58, which is less than 67. Therefore, the web is not susceptible or subjected to the shear buckling. Therefore, the check for the buckling need not be done. Need not be done. However, if you want to calculate the load carrying capacity of the web under the buckling criteria, then you please go to class 8.7.3.1, page number 67. Let me go to this page number 67, student, right? Not this, right? Page number 67. Yes, let me go to the page 67. 67. Yes, not this one. 67. This page number 67 is this one, right? Sorry, right? This is the page number 67, student, right? As per class 8.7.3.1, the check for the web buckling criteria should be done. However, here it is not required, therefore I am skipping off. However, I'll illustrate this in the next problem, right? In the next problem, right? Now, once this check is also over, therefore now I'll say that the check for web buckling is not needed. However, whether the check for crippling is needed or not, right? Let me show what is a check for web buckling and check for web crippling, right? Using this schematic, student, right? This is how when the beam is subjected to load, it will try to buckle like this, right? Therefore, this is what the buckling. However, here this check is not needed now. Therefore, I'll just skip it off, right? That will be done like this. The calculations will be done like this at a dispersion of 45 degree at the neutral axis. What is that? Width is equal to B plus N1, or if it all is under the concentrated load, B1 plus 2N1. However, I'm not requiring this. I'm skipping off this. Then what is the check for crippling? Check for this is check for buckling under the concentrated load, B1 plus 2N1. I don't require this. This is at the support, B1 plus N1. Therefore, the central part of the web is buckling, as if a column which is fixed between the two ends like this. Therefore, this is the check for buckling. I don't require here because it is less than 67 times. This is the check for crippling. However, at the intersection of the flange with the web, right, a local kink will form like this, which is called the crippling. Right? Therefore, that should be done like this, right, over a width of the base plate, because the beams will be resting over the base plate. Regular beams are now, this grillage is resting, is supporting the load from a base plate of its size is given. Therefore, that should be taken now, right? Therefore, that B plus N2. However, that N2 should be calculated with a slope of 1 in 2.5. Right, 1 in 2.5. Therefore, it goes up to the end of the root radius. Therefore, there is a thickness of the plane plus R1 multiplied by 2.5. Right, and that now I'll show. Those calculations. Right. Therefore, if I come to that calculation, as per this class 8.7.4, page number 67. Let me go to that page number 67, student. Right, the same page. Right, bearing stiffeners. Right, the should be done. The bearing strength of the web, Fw is equal to B1 plus N2 multiplied by thickness of the web multiplied by Fyw divided by gamma m naught, where B1 is the stiff bearing length and N2 is the length obtained by dispersion through the flange to the web at the junction at a slope of 1 in 2.5, just now shown in the schematic, right, to the plane of the flange, and Tw is the thickness of the web and Fyw is the yield stress at the web, right. Using this, now let me calculate the numeric value. Therefore, that same formula I have written, where N2, I already explained what is this, is N2, right, like this, right. This is N2. What I am getting is N2, which is nothing but the thickness of the flange multiplied by thickness of the flange plus the root radius, or this itself is H2, right, H2, that multiplied by 2.5. However, we are having a base plate. Therefore, that base plate is transmitting the load on either side. Therefore, 2 times it is transmitting on 2 sides. Therefore, 2 multiplied by 2.5 multiplied by H2. H2 for this beam section is equal to 34.9. Or alternatively, what you can do is thickness of the flange plus root radius. Both are same, right? Therefore, now I'll get N2 as say 174.5. Therefore, the crippling load, web crippling load, is equal to B1, the base plate under the first column. First column base plate is equal to 800 mm by 800 mm, student, right? Therefore, plus 174 at the intersection up to the end of this root radius 174, right, N2 multiplied by thickness of the web, thickness of this web 9.2 multiplied by 250 divided by 1.1. Therefore, at this intersection of the flange with the web, whether a local kink will form or not, that we are finding out by means of this crippling load. Therefore, web crippling load will now work out upon dividing with 10 to the power 3. I'll get 2037.59 kilonewton. However, it is just subjected to a small shear force of 326.25 kilonewton on each of these beams, 3 beams. Therefore, it is okay in crippling criteria, Web crippling criteria also. Therefore, since this beam, what we have assumed, which is a trial beam, what we have assumed, this trial beam as ISLB 500 at the rate of 73.5 kg per meter, which was a trial section, has passed all the checks, therefore that section itself is my final section. Therefore, provide 3 ISLB 500 at the rate of 73.58 kg as the final section under the column 1. Similarly, now let me go to the design of the first tier beams under the column 2, second column, under load P2. Therefore, now I'll initiate that second design of the top tier grillage under the load, under the second column, under the load 2. Therefore, now I'll do the analysis first. First heading is analysis. Therefore, that shear force, these are the factored shear forces, students, right? And factored design forces, right? VU2 or V2U is equal to P2 divided by 2L, L minus L2. Factored load is equal to 800 divided by 2 multiplied by 3.7 multiplied by 3.7 minus 0.7, because the base shear, base plate under the column 2 is 0.7 by 0.7, right? Therefore, that divided by 10 to the power 3, if this is already in terms of kilonewtons, therefore it now works out, say, 729.72 kilonewton, right? Similarly, what is the factored bending moment? It now works out, say, P2U divided by 8 multiplied by L minus L2, 800 divided by 8, 3.7 minus 0.7, right? It works out, say, 675 kilonewton meter. However, we already designed the previous section. Let me see what is the bending moment. Right there, the previous section could able to resist up to 350.72, right? Therefore, I want to proceed with the same section, ISLB 500. Or further, if you want to optimize, you can do another loop also, right? Therefore, I don't want to optimize now. Therefore, I'm assuming if you want to optimize, you can use a lower section also, but I don't want to optimize. Therefore, I'm assuming the same three numbers of ISLB 500 at the rate of 73.58 kg per meter as my final sections, because it is able to resist. Because now the bending moment on each of the beam is equal to 675 divided by 3 means 225 kilonewton meter only, whereas the previous section could able to resist a bending moment of 350.72. Hence, I am proceeding with the same section. Therefore, other checks I'll skip off because I have not all used the other section. Hence, I am skipping off the other checks. If you are choosing a section other than this previous section, you need to do all these checks, right? Check for spacing, check for shear, check for low shear, check for movement, design capacity, right? And check for web buckling, check for web crippling. All these checks you need to do. However, I'm skipping off because I'm using the same check, same section. For the top tier grillage, I have used for both column 1 and column 2. Under the both of these columns, use 3 ISLB 500 at the rate of 73.58 kg per meter. Right now. Now let me go for the analysis of the low tier beams. Before which, now I need to calculate what is the factored intensity of the load. QU is nothing but, right, factored load. Factored load is equal to 800 plus 2700 divided by the area of the footing provided, 6.8 multiplied by 3.7. Therefore, it works out say 178.85. This is the factored intensity of the load, student, right? Whereas the actual intensity of the load, that divided by 1.5 means 119.24 only, whereas the permissible SBC is 200. Therefore, this 119.24 is much less than 200 kilonewton per meter square. Therefore, it is okay. Or alternatively, what you can do is, because I got just 2.93, I have provided 3.7. Therefore, I am getting this intensity of the shear. Intensity of the shear is approximately 120, which is much less than 200. If you just reduce this 3.7 to say 3 meter, then obviously this value will increase from 120 to maybe some 160, 170, which is less than 200 kilometer in such case also. But I don't want to do that. I want to proceed with say 3.7 meter only. Therefore, the actual intensity of the shear, actual intensity of the soil pressure is equal to 119.24, which is less than 200 kilometer per meter square, and the factored intensity of the soil pressure is equal to 178.85 kilometer per meter square. Now I'll go with the analysis of the lower tier beams. Right? Now let us consider a section 2.2 like this, right? Let me show this a section 2.2 student, right? This is what I'm doing, right? This is a section I'm considering within this left side base plate, right? A section within this base plate, right? Actually there is a concentrated load here, right? The section may be from left end of this base plate to the right end of this base plate, right? Anyway, therefore if I consider a section here 2.2, then how now I'll write a generalized equation. Then I'm writing that generalized equation, student, right? Therefore the shear force at that section, just wait, right? At that section is equal to Vx is equal to QLX minus P1 by B1 x minus 1.4, right? From the schematic, right? What I have shown, right? Similarly, the bending moment is equal to Q multiplied by L is the intensity of the load multiplied by acting over a distance of x, or that is concentrated at a distance of x by 2, right? That minus P by B1 multiplied by x minus 1.4 multiplied by x minus 1.4 divided by 2. Therefore that is the x minus 1.4 divided by 2 whole square, right? Therefore now x minus 1.4 multiplied by x minus 1.4 divided by 2. It is not that whole divided by 2, so right? X minus 1.4 whole square divided by 2. Therefore, however, we already know that maximum bending moment occurs when shear force is equal to 0. Means if I equate this to equal to 0, now I'll get say solving with, now I'll get x is equal to 1.74 meters. However, let me check, is it just greater than that net cantilever projection A1 prime? Yes, net cantilever projection is 1.8 minus the width of the base plate is equal to 0.8 divided by 2. Therefore 1.8 minus this 0.4, yes, A1 prime, it is greater than 1.4 like this, right? Let me show this, right? It is just greater than A1 prime. That section must be starting from this. This is the lower bound. This is the upper bound of that section, right? It's just greater than A1 prime, which is 1.4 meter. And is it less than this the upper bound? This upper bound, right? This upper bound is equal to, right? A1 plus this with B1 by 2, that upper bound value, right? Therefore that numeric value will now work out, say 1.8 plus width of the base plate is equal to 0.8 divided by 2, 0.4, therefore 2.2 meter. However, you please see that the section X 1.74 is just greater than 1.4 meter, this 1.4 meter, right? This section X is just greater than this and less than this upper bound, right? Therefore there is no error in calculation. If this is not satisfied, means that indicates that there is some error in the calculation. There is no error in the calculation of the shear force nor that of the bending moment. Therefore now if I substitute this value in the previous formula, now I'll get the maximum bending moment into this formula as, say, a value 904.21 kilonewton meter. 904.21, because now I have decided what is x, right? Therefore previously the bending moment was written in general equation, x square divided by 2 or x minus 1.4 square divided by 2. Therefore upon substitution I am getting 904.21 kilonewton meter. And similarly now I'll calculate the shear force as a VU, the maximum shear force as say 178.85 multiplied by 3.7 multiplied by 2.2 at the right, minus 2700. This is under the second column. Student, right? 178.85 multiplied by 3.7 multiplied by 2.2. Previously it was under the first column, right? Therefore that minus 2700 by 0.8, 2.2 minus 1.4. Therefore it works out, say, minus 1244.16 is the shear force under the second column. Therefore I got the shear force on the left part, right, as well as on the right part, right? At the I got the shear force as 1244. I'll show that variation also. 1244.16 here like this, right? 1244.16, right? Sorry, right? Here I got the 1244.16. Let me show that variation of the shear force, right? And now let me also consider for the analysis a section 5.5 like this, right? Section 5.5, right? Section 5.5, right? Now just now I got this maximum shear force 1240, because that shear force will be changing its sign, right? There is a SFD, shear force diagram, as well as the bending moment diagram. This now I already got the maximum bending moment as the value what I have got, that I have noted down as that maximum bending moment is equal to 904.21. Therefore once I get these, now I'll draw the shear force and bending moment diagram also, as I have shown already, right? Then let me go to this section 5.5. There now the shear force Vx is equal to this QLx plus 1800 divided by 0.7 multiplied by x minus a2 prime under the second column, right? This is under the second column, where a2 prime is this one. I am just analyzing under the second column where the maximum shear force will occur, right? Therefore upon analysis under the second column, now I'll get the maximum bending moment also under the second column, given by this QLx multiplied by x square x by 2 plus that load 800 divided by 0.7 multiplied by x minus a2 prime divided by 2. However, for maximum bending moment, the shear force must be equal to 0, equating with, now I'll get under the second column x must be 0.89. Here the x is taken with reference to the right hand side. X is taken from the right hand side. Reference is the right hand side. Here this x is with respect to this, right? Here 0.89. Yes, correct, right? That 0.89 is greater than 0.65 plus 0.75 means 1.35. Therefore that is correct. Whereas, right, this is 0.89, right? At this section you get the maximum bending moment. In the previous case I got the maximum bending moment at a distance of 1.74 meter from the left hand side section, whereas this is from the right hand section. This 0.89 is from the right hand section. Therefore that is once I get this maximum the location where I'll get the maximum bending moment. Now I am checking, I have already checked that, right? Therefore this x 0.89 is greater than 0.65 meter, which is a2 prime, and it's also less than that upper bound value of 1 plus 1.35. Therefore okay. Once I get this 0.89, then I'll substitute into the above formula for analyzing the design forces under the second column. M2, maximum bending moment under the second column, is equal to, upon substitution I'll get this result as 188 minus 188.02 kilonewton meter, 188.02 kilonewton meter. However, out of these, the maximum bending moment under the left column is maximum, because that was 904.21 kilonewton. However, even there itself I got the maximum shear force. You please see, it was 1244. However, under the second column, I am getting hardly a mere small value of 188 kilonewton meter bending moment, and obviously upon substitution you will get a small value of shear force only. Therefore, this will not govern the design. This will not govern the design for the section. Only the left hand side column, under that the analysis, that will govern the design. Therefore, now I am showing the SFD and BMD like this. Therefore, this is what the analysis I have done, right? At 1.74 meter I am getting the maximum bending moment. Maximum bending moment, that value is equal to 904 point odd value, right? Or this SFD is a linear variation. The bending moment diagram is 1 degree higher, quadratic variation, with a maximum value of 904 point odd value, and it is reducing to 648.09 after changing the curvature, and just below this second concentrated load, that hogging bending moment is equal to that. Just now we have seen that just 188 negative bending moment is equal to 188.02. However, here I am showing that as positive bending moment. That cantilever bending moment itself is negative bending moment. However, I am showing in the drawing as this schematic as positive and this as negative, right? This negative is positive bending moment actually, right? The positive bending moment is equal to 648.09 kilonewton meter. Similarly, the shear force diagram, shear force variation diagram is like this, right? 920 at the face of this 1.4 meter to at the end of this base plate, it is going to 1244.57, whereas to the other side end of this it is going to some numeric value, whereas these are small values compared to the top. The analysis on the left hand side. Therefore, I am not writing the ordinates now. Just I have shown the variation of the SFD only, right? Therefore, these are my governing design forces, and this is also my governing design force, right? 900 odd value, right? These bending moments will not govern. Therefore, once I have analyzed and fixed what are the governing design forces, then I'll go for the design of the second tier. Therefore, now let me start the design. Next heading is the design. Therefore, once I say the design, therefore as per IS 800 2007 class 8.2.1.2 page number 53, assuming plastic section and low shear. Already have explained in the previous subheading, student. I will not go with the codal specifications now. Alright. Therefore, now the plastics, the required plastic section modulus upon substitution, now we will get 904.21 10 to the power 6 divided by 250 divided by 1.1, or say it works out say value 3978.52 10 to the power 3 mm cube. However, because the lower tire, in the lower tire I can assume many number of beams like this, right? In the low, just now I already assumed designed the upper tire with 3 ISMB 500. In the lower tire I can assume over this 3.7 meter I can assume many number of beams like this, right? 1 2 3 4, many number of beams. Whereas in the upper tire, just within a distance of 0.8 I cannot assume many number of beams, hardly say 3 or 4 only, right? Therefore, this is how in the lower tire I can assume more number of beams. I am assuming 10 number of beams. This is my assumption. Therefore, by assuming 10 number of beams, the plastic section modulus required for each of these beams is equal to 3978.52 divided by 10, or say 397.85 10 to the power 3 mm cube. Whereas for the trial section I will increase this value by 20% extra. Therefore, 1.2 multiplied by 397.85, it works out say 477.42 10 to the power 3 mm cube for the trial section. Once I say the trial section modulus, then I'll fix a trial section from IS 800 2007 table 46 page number 139, already shown in the previous subheading, or alternatively from SP 61 1964 table 1 page number 2, or let me go to this table page number 139 ISMB 250 as per 139 ISMB 139. Yes, this is 139 ISMB 250 at a rate of 37.3. I am just noting down the relevant property, student, right? The plastic section model is equal to 465 and other properties also. I just noted down those relevant properties, student, right? You may please see that. Already noted down. The plastic section model is equal to 465.71 10 to the power 3 mm cube, which is greater than the trial section modulus plastic section. The plastic section model is required for the trial section, which is required is 477. Almost it is here and there, approximately same. Therefore, I'll proceed with this. And I'll note down the other properties, right? What is the width of this flange is equal to 125 and thickness of the web 6.9, and H2 is equal to 27.95 and thickness of the flange. Thickness of this flange is equal to 12.5 and root radius R1 is equal to 13, and also the elastic section modulus also Z, right? Therefore, once I do that, now I'll do the very first checking, check for the spacing, right? However, I do have the length 3700 mm is provided already, within which I want to provide say 10 number of beams, right? Within this 37, from this end to the other in 37, I want to provide say 1, 2, 3, 10 number of beams, within which only 9 spacings will be there. Therefore, what is the actual spacing provided? What is the actual spacing, sorry, available, not available, right? That is 3700 minus 10 multiplied by 125, which is each of the flange width, that width by 9. It works out say 292.2, which is greater than 75 mm. Therefore, okay, it is okay in the first check. Similarly, as per this class 8.4, page number 59, check for the shear. Check for the shear. Just now we have seen already in the previous subheading. You just go through that. Therefore, now I'll say the design shear force VD is equal to Fy TWH divided by root 3 gamma m0 upon substitution 250 multiplied by 6.9 multiplied by 250 divided by root 3, that divided by 1.1, that divided by 10 to the power 3. In terms of kilonewton, it works out say 226.34, which is much greater than the shear on each of the beam is just 1244.57 divided by 10, means 124.45 kilonewton only. Therefore, each of the beam can resist up to 226.34, whereas the factored shear force coming onto each of the beam is 124.45 kilonewton only. Therefore, it is okay. Once it is okay in that second check, now I'll go for the check for the high shear. As per IS 800-2000, class 8.2.1.2, page number 53. Because here this actual shear force 124.45 is less than 0.6 VD. What is 0.6 VD? Is 0.6 multiplied by 226.34, which is 135. It is a case of a low shear. Therefore, the exact calculation for the design capacity of the section need not be done by taking into account the shear. That is what the conclusion. Therefore, as per that conclusion, now I'll say MD is equal to MD only. Therefore, next check is a check for the design movement capacity as per IS 800-2007, class 8.2.1.2, page number 53, assuming plastic section and low shear. Therefore, beta is equal to 1 for the plastic section. Now, before that, I need to do what is the section classification as per this table 2, page number 18 of IS 800-2007. Then B1 by TF. However, I do have B1 here. The width of the flange is equal to 125 divided by 2. That now works out say a value 62.5 divided by thickness of the flange 12.5, which is much less than 9.4. Hence, the flange has plastified. Similarly, whether the D by TW, now 250 minus 2 multiplied by 12.5 plus 13, that divided by 6.9, which is equal to 28.84, is also less than 84, means entire web has also plastified. Hence, the entire section is a plastic section. Hence, MD, design movement capacity, design or bending capacity or movement capacity, MD is equal to 410.5. That multiplied by 10 to the power 3 is the plastic section modulus, multiplied by Fy divided by 1.1, 250 divided by 1.1, right? Therefore, that divided by 10 to the power 6, it works out say 93.29 kilonewton meter, whereas it is greater than 90.42 kilonewton meter to which it is subjected, right? Therefore, it is okay. It is okay. And also, next check is check for web buckling. However, here, as per class IS 800 2007, class 8.2.1.1, page number 53, because the D by TW, which is 28.84, is less than 67, this one is less than 67, the web buckling check need not be done as per this class 8.2.1.1 of page number 53. However, if at all it is required, you should do as per the class 8.7.3.1, page number 67. However, I will illustrate that in the next problem if at all that is required. Now, the last check is a check for web crippling as per class 8.7.4, page number 67. I already shown in the previous subheadings, right? Therefore, now I'll get the crippling load in the web given by this formula B1 plus N2 multiplied by thickness of the web divided by gamma m naught. Upon substitution, I'll get say B1 plus N2. How to calculate N2 I already shown, right? Now I'm getting N2 is equal to 139.75 here, like this, right? This N2 is like this, right? Here, this N2, right? This is that N2 at a dispersion of 1:2.5 student, right? Therefore, that N2 B1 plus N2 divided by 1.1, 800 plus 139.75 divided by 1.1 multiplied by 6.9 multiplied by 250, that will be 10 to the power 3. It works out say 1473.69 kilonewton. However, the shear force on each of the beam is just 124.45 kilonewton only. Therefore, the web will not fail in crippling criteria, like this, in crippling criteria. Therefore, it is okay in web crippling also. Therefore, because it is okay in all the criteria, therefore my assumed section, right, my trial section, which was ISMB 250 at the rate of 36.59 kg per meter, 10 numbers is okay as a final section, as shown in this figure. I'll show that figure to it, right? There is a final design of this combined rectangular glazed footing, student. I hope you enjoyed the discussions what we had in today's class, right? If you have really enjoyed, right, don't forget to click like, share, subscribe to our YouTube channel and help our channel to grow. We'll meet in the next class with another discussion on combined trapezoidal glaze foundation. Till then, bye bye students.